Hello, today we are continuing to look at redox reactions. These reactions are sometimes written in a diagram like this. And this diagram shows the first letters of these processes, oxidation, reduction. As we found out in the last lesson, these are very complex processes in which electrons are moved from the element that gives up electrons to the element that accepts those electrons. Let's remind ourselves how and what processes are involved. Let's say we have the metal magnesium interacting with each other. Now let's be sure to note here that magnesium is a solid and it reacts with copper oxide. Copper oxide is also a solid. This process itself is heated, so without heating, the reaction between the two complex substances will not be possible. As a result, magnesium will replace copper in this process, take its place, and magnesium oxide is produced. And the second substance, the product of the reaction, will be copper. Copper is a solid, as is magnesium oxide. So, let us understand what kind of processes occur in this case, what they will be called. In order for us to figure out what exactly is going on, we need to put the oxidation degree charges. So magnesium has an oxidation charge of 0 because it's a simple substance, an element. In Cupermo, we have to give oxygen 2 minuses, copper 2 pluses. In magnesium O, oxygen has 2 minuses, magnesium has 2 pluses, while copper will have a charge of 0. Now, what are the next processes that take place? So, magnesium is the element that's going to go to charge 2 plus in this case. So, it loses electrons. In this case, it becomes magnesium with a charge of 2 plus. It goes into the ionic state and will give up 2 electrons. But I have already explained in the previous lesson that the record of giving up electrons is not shown on the left side. The record is not accepted to show it, but it is written exactly like this. On the right side, show that the electron in this case will be given up. 2 electrons. Next, what is the copper at this time? Copper will go from oxidation degree 2 plus to oxidation degree copper with a charge of 0. And then the copper, it turns out, will accept 2 electrons. So magnesium will give up 2 and copper will take up 2. In these processes then, it cannot be the case that both elements are giving up electrons or both elements are accepting them. In a redox process, it is customary to conclude with a specific record, placing the found electrons behind a vertical line. This post-process recording of electrons is a standard practice in understanding redox reactions. We have the option to swap them, but it is unnecessary since they are identical. Consequently, our basic coefficients in this situation remain at 1. It is evident that there are no additional coefficients needed in our equation. Now, let us determine the processes that have occurred here. Magnesium loses electrons, hence this process is referred to as oxidation for magnesium. And magnesium itself in this case is called a reducing agent. The entry then goes like this. This element will be reducing agent, or write it down like this. Now what will copper be at this time? For copper, this process is called reduction. And what is the name of the copper in this case? This element will be called then oxidizer. And the entry in this case is made like this. So, and the entry that I showed, the given equations that are shown here and here, these are called half reactions. which are written in this form, and this entry itself is called half reactions, electron half reactions. Now, as we dig deeper into our investigation, we can dismantle this process and unravel its inner workings. Starting with a solid, charge-free magnesium, we witness its reaction with copper oxide. However, to better understand this phenomenon, let's delve into the composition of copper oxide, showing that it would formally dissociate, break down into copper and oxygen. And on the right-hand side, magnesium O will also behave. It will go into magnesium O solid, into oxygen, which is also solid, and you get copper, which is also solid. Now let's see that in this connection, on the left and on the right, we have oxygen with a charge of 2-, which we can regard as similar. Such particles, which we can subsequently reduce, are called
reducible particles,
or like particles that we can eventually, if we proceed in this manner, our equation will ultimately be simplified. The equation represents the reaction between solid magnesium O combined with magnesium, which has no charge, and solid copper, which is an ion known as Cooper 2+. The result of this reaction yields magnesium ions with a charge of 2+. Well, copper will also be released, which is solid in this case, and pay attention, in such a process, in such a reaction, it is clearly visible that indeed magnesium has passed into the magnesium 2+ particle, well, and copper respectively has passed from 2+ to 0 charge. Thus, redox processes are a very complex structure. The transition of electrons in this case occurs from metal magnesium towards metal copper. I would also explain the question of why magnesium is able to displace copper, why this happens. The fact is that for metals, there is a special series of metal activity in which magnesium is in this series earlier than copper. Or one could say that magnesium is stronger than copper, and then magnesium can displace copper from its, for example, oxide, or for example, another compound, for example, there can be salt. Metals have such an ability to be reducing agents in relation to metals that are weaker than them, and then such a metal will certainly displace a weaker metal. And I draw your attention, but the reverse process in this case would be absolutely impossible, because copper will never be able to displace magnesium back. This reaction will not be possible under any circumstances, because metals have the concept of metal strength, and then a stronger metal can displace a weaker one, but not vice versa. So today we looked at the redox processes. Now we have figured them out in more detail. I hope this is understandable. Well, in the next lessons we will learn how to select coefficients in such equations using a special method, the electronic balance method. Well, that's it for today. Goodbye.